This is 2013 AMC 10B Problem 22. The regular octagon ABCDEFGH has its center at J. Each of the vertices and the center are to be associated with one of the digits 1 through 9, with each digit used once, in such a way that the sums of the numbers on the lines AJE, BJF, CJG, and DJH are all equal. In how many ways can this be done? Okay, so basically, so basically, in this problem, realize that the sum of the numbers on AJE would be A plus J plus E. For BJF, it would be B plus J plus F, etc. Every sum includes a J, so we don't really care what J is, I guess, for now. For now, we don't really care about what J is because, as long as J is a constant value, then these J's can all be cancelled out. We only want to care about A plus E equals B plus F equals C plus G equals D plus H. Okay, so how do we make this actually happen though? So firstly, we choose a value for J, and then we're supposed to match the remaining 8 numbers, because there's digits 1 through 9, the remaining 8 digits into pairs that are symmetric. So, for example, if I chose J, if J is 1, then I can make, then there are 4 symmetric pairs, right? That I can plug into A, E, B, F, C, G, and D, H. There will be 2 plus 9, 3 plus 8, 4 plus 7, and 5 plus 6. So I can plug these pairs in. So now what we're going to think is that there are 9 different options for J. J can be 1 through 9, and there will always be 4 symmetric pairs for the 8 remaining values. But that is not true, because, for example, when J equals 2, this just does not work. There's no symmetric pairs. Because when you want symmetric pairs, what you're going to do is pair the smallest number with the biggest number, the second smallest number with the second biggest number, so on, until you reach the middle numbers, right? So let's do that. That's just 1, 9. Okay, that sums up to 10. And then 2 is gone, so 3, 8. But that sums up to 11. So this just doesn't work anymore. So this just doesn't work. So we've got to find the values of J for which there are 4 symmetric pairs. Well, 1 is a value because it's at the leftmost of the number line. We can also take J equals 9 because it's at the rightmost. So you can pair up 1, 8, 2, 7, 3, 6, 4, 5. And we can also pair up, so we can also have J equals 5 because that's the middle value. So you can have 1, 9, 2, 8, 3, 7, 4, 6. So there are 3 values in total that work. Okay, so there's 3 ways to choose J. And there are 4 symmetric pairs after you choose J. So we want to assign the 4 symmetric pairs to A plus A, E, B, F, C, G, and D, H. Well, there are 4 factorial ways to do this. For A plus E, you have 4 ways to choose a symmetric pair. And for B plus F, you have 3 ways to choose the remaining symmetric pairs, etc. And then, last but not least, you also have you can also switch the numbers around in the pairs. If AE was 2, 9. You can also switch them around, and this can be 9 too, which also works. So there's 2 ways for each symmetric pair to reside in one of the sides. So there's 2 to the power of 4 ways for the switching thing to make a different case. So we multiply these up. This is 3 times 24, which is 72 times 16. 72 times 16. 2 times 6 is 12. 6 times 7 is 42, plus 1 is just 43. 1 times 2 is okay, so this is just 72. So this is 3 plus 2, which is 5, 4 plus 7, which is 11. So this is the answer because, can't really think of any flaws in the logic, so I'll just go with the answer, and it's in the answer choices anyways.